the recording. Okay, so our recording has started. All right, and let me give you a moment to copy this example down. Okay, so here we want to estimate the sum of this particular series correct to 3 decimal places. Now this series is not a telescoping series, it's not a geometric series, so it's not, there may be a formula to find the sum of the series in an advanced book. There are whole books written on infinite series and formulas and so forth. Actually, I actually can find the sum of this hold on here, the sum of that series actually, but I'll tell you how later this week. Okay, we need a little more. You need a little more knowledge, but at any rate, right now we want to estimate the sum of the series correct to 3 decimal places, and we notice that this is an alternating series with the -1 to the nth power as n goes through its values. And when n is 0, -1 to the 0 is 1. When n is 1, -1 to the first is -1. When n is 2, -1 squared is +1. So it's an alternating series. All right, so there is a theorem called the alternating series estimation theorem, which you encountered in your homework, that says that if it says if you have a convergent alternating series. And remember from the alternating series test that for an alternating series to converge, the terms of the sequence have to be decreasing with n as n gets larger, and that's the first condition. And then the terms of the sequence have to approach 0 as n gets large. So if you have a convergent alternating series, and that's when they say the sum of the series satisfies these 2 conditions, They just mean if you have a convergent alternating series. In that case, if you were to consider the nth partial sum, which would be the sum of the first n terms, and approximate the true partial sum, which is denoted by S, the difference between the true sum, the sum of the series, the difference between the sum of the series S, okay, and the nth partial sum, that the difference between the true sum and the approximation, which is the nth partial sum, that error, that remainder, is going to be less than or equal to the n plus first term of the series. Okay, and that has to do because you have an alternating series. That has to do with the fact that you have an alternating series. So let's look at the solution to this. Okay, and this is from the textbook. So this one I felt textbook was very good. So I just copied from the textbook. So the first two steps establish that this is an alternating, that this is a convergent alternating series. To get a feel for how many terms we need to use in our approximation, we write out terms of the series. So here they've written out 8 terms of the series, okay? 8 terms of the series. But this, well, all right. And are there any questions? You know, they're just enumerating the terms of the series, and then they're computing the factorials, and that's how they get all these fractions here. Are there any questions on this step right here? Are we so far? Are we good with that? Okay, and all right. So they say, notice that b sub 7, which is 1,501 over 5,040, is, well, they're being a little bit I guess mathematically beautiful about it, you might say. But if you put this on your calculator, you're going to get 1.98 times 10 to the negative 4th. 1.98. If you 1 divided by 5,040 is 1.98 e negative 4, which is 1.98 times 10 to the negative 4th. So that's 0.0001998. And they, I want to say this the right way. So they call that term B7. So, but if you look at the series here, you have 1, 2, 3, 4, 5, 6, 7, 8 terms of the series. But what they're doing is, because the series started at n equals 0, they're calling this first term B sub 0. Okay, they're starting at B sub 0. And then the second term here, they're calling B sub 1. And so the 1 over 7 factorial, they call it B sub 7. Okay. But the point is that the 8th term, which they call B sub 7, is 0.000198. And that's not going to affect the third decimal place. That's not going to affect the third decimal place. if you, and so by this alternating series estimation theorem, the sixth partial sum, but it's the sum of they call it S sub 6, but it's really the sum of the first 7 terms of the series. That's gonna be 0.368056, and we know the difference between the true sum S and this S sub 6. The sum of the first 7 terms would have to be less than or equal to the 8th term, B sub 7, and therefore you have it correct to 3 decimal places. You have it correct to 3 decimal places. So that's how you use this. You have to go out far enough. You have to take enough terms of the series so that you reach a term that won't affect the third decimal place. Because notice here you have, this here you have 3 zeros with the 2 there, and that's less, by the way, than 1 over, no, that's less than 5 over 10 to the 4th. So you stop, since it's 3 decimal places, we stop when we reach a term that's less than 5 over 10 to the 4th. And again, that 5 is there on top because you could have a rounding issue that affects the third decimal place. But if the term in the alternating series is less than 5 over 10 to the 4th, in this case, you won't affect the third decimal place. If they were to ask, get the estimate correct to 4 decimal places, then you would want to look for the term that's less than 5 over 10 to the 5th. Okay, are there any questions on that so far? All right, you can just ignore the phone there, ignore that. 1 over 720 and as you know, I have a landline at home, so okay, the 7th term of the series was 1 over 720, and that equals 0.0014. Well, notice that's greater than 5 over 10 to the 4th. 5 over 10 to the 4th is 0.0005, right? So so see that term using that term is the 7th term of the series, because it's greater than 5 over 10 to the 4th. We can't stop there. But when we get to the 8th term of the series, 1 over 5040, since that term is less, this is less than 5 over 10 to the 4th, right? So I'm really not worried about this too much. I'm not worried about that too much, okay? I'm just looking at that 8th term, B sub 7. It equals 0.000198. That's less than 5 over 10 to the 4th. Therefore, that means that the first 7 terms of the series, if you add them up, you will get an approximation that's accurate to the true sum of the series, correct to 3 decimal places. Okay, so does that make sense? Are there any questions on that? I'm not really worried about the 0.0002, but okay. Was this helpful? Was this helpful, this little discussion? Maybe give a thumbs up if you think it was. Thank you, Raymond. All right. Are there any questions? Any questions on it? You have to let me know. Okay. Okay. Well, then let me stop this recording here.